Good morning, everyone. I hope that everyone is feeling well. So we are in the computer vision course, and we will start edges, corners, and lobes today. I hope everyone can hear me. Can someone confirm that I can be heard?
Yes, sir.
Okay, thank you very much. Um, so we have been studying about Gaussian smoothing and other spatial filters. So this is the next step of those spatial filters, where we try to apply those filters to detect edges, corners, and lobes. This is a very important lesson because based on these, people detect features and they describe these features using signatures, and they can then use these to align images, make 3D reconstructions, and even do things like robot navigation using techniques like visual slant. So we will get started with this. First of all, let's look at edge detection. You can see here, this clearly is an edge. So you can see a sharp transition from white to black is an edge and so on, right? So for example, when people do drawings, so they use edges to draw because people's eyes are very sensitive to these edges. So because these edges contain more semantic and shape information, so it is more valuable and more compact than the pixels. So they give rise to due to depth discontinuities. So you can see this is the foreground, and beyond that is the background from here. And here you can see the surface normal discontinuity. That means the perpendiculars to this surface change in sign there. And then here you can see a surface color discontinuity. Here it is an illumination discontinuity. So due to these reasons, you can see edges. So now let's consider this image. Now this image has a black stripe, right? And we will take this scan line. This is called a scan line. So actually, it turns out to be a one-dimensional image. So here you can see bright intensities, and here you can see dark intensities, and here you can once again see the bright intensities. Now, if I ask you this question, draw me a graph of the intensities. Now consider this axis as some axis. Let's consider this as the y-axis, and in the vertical axis, draw the intensities, image intensities. How would you do that? So starting from here up until there, we can draw the intensities. So here in this region, the intensities are quite dark. So in this graph, what you will get is 0. Oh, it's not dark, it's bright. So you will get 255, right? 255 in that region. So I will draw it again, starting from here, this horizontal axis, and going up until here. And sort of here we can see the transition from bright to dark. We also transition from bright to dark. And if I draw these intensities, you will see high values over here, low values over there, and high values over here. And this transition is not very sharp. So it will go like that, like a smooth transition from dark to bright. I hope you can agree. So this value maybe is 255 because it is the brightest, and this value is the darkest, it's 0. So this axis is in intensities. This axis, we consider this so-called scan line. This direction is the y direction. I hope that's clear to you. If you have any question, as usual, you can of course turn on the mic and ask, and also you can type in the chat. So I'll be able to answer. I'll be very happy if you ask any questions. Okay. All right. Now this is, I think you will agree with that. Along the scan line, this is the intensity profile or the intensity function that you get. Now, what is an edge? You can see here we have an edge, and here we have another edge. So these edges, you can see, correspond to sharp transitions in the intensity value. Sharp transitions signified by going from this very positive values to very negative values here, and very positive values 255 actually, to very from very negative values with zero values to the 255, that transition. So how do you signify a transition mathematically? So mathematically, the transition is signified by the d by dx, right? First derivative, first derivative. So you take this along this axis, you take the derivative. So there'll be a high derivative here, and there'll be a high derivative there, which correspond to the edges. So you can see here going from a positive value to negative value. So you can see the slope is like that, right? If I draw a line like that, slope, of course, it changes. So this you can see has a negative gradient. If you take this line, it's like that. It has a positive gradient, right? A small angle with x-axis, you know, is a positive gradient. A large angle with x-axis greater than 90, you know, it's a negative gradient. So this is that, and this is that. So if you want to detect edges, you detect extrema, maxima, or minima in the derivative. So now the theory is clear. Now we have to practically implement this and see whether we can get actually the edges. But now let's look at these expressions for obtaining these edges. And these things we have done for our A levels, I think. So let's look at this. Now, how do you, if you have a function, if you have a function, and this, let's call this the x-axis, and this is my fx, the function fx. Now, I want to find the derivative of this function, or the differential coefficient of this function um, at some point, let's say, at particularly x naught, x naught. So what do? I take a small change from x naught, another point here. So this point is actually x naught plus epsilon. Let's take a small number called epsilon. This epsilon is a small number. Sometimes people use h for that, epsilon. So what is the value of the function here? And what is the value of the function there? Of course, it's clear. At this point, the value of the function is fx naught. Fx naught. And here the value of the function is, I will write it here, f x naught plus epsilon. Right? At that point, the value of the function. Yes. So how do you get the slope of this? Consider this as a triangle, right? We consider this as a triangle like that. And now we want this distance and this distance. These two distances we take and we divide. This is what we do. So there you go. So the derivative will be f at this point x naught plus epsilon minus fx naught, yeah, divided by this distance. This distance you can see is epsilon, right? This distance is epsilon. So I don't have to write the epsilon. But you can see, as we change the point x naught from one point to another, this derivative changes. So that's the thing about the derivative. So, and also these 2 points, when they are far away, you sort of get an average derivative. What you want is average value of the derivative. What you want exactly is when this epsilon is as small as possible, right? We want that. So therefore, that's why we take the limit epsilon goes to 0. So this is what we have studied in our A level. It's very simple. So therefore, for an image also, it's the same thing. But remember, image has two dimensions. So what we had to do is we had to fix y, right? We cannot consider both of them at once. So we had to fix y. Now y is fixed, and we have only changed the x coordinate. You can see there's exactly the same thing we have done, but because it has two variables, x and y, we had to use the this symbol. Dharma symbol to indicate the partial derivative. Can you enable quiz 5 on fitting and alignment, because most of the students miss that quiz to do. I don't know why, but I will enable. Okay. These quizzes are just there to check your, to help you to understand whether you have gone through the material well, okay, understood the material. I mean, there's no value in those quizzes other than that, because they are very, very simple quizzes. Assignments are the more important ones. Assignments I mean, if you do the assignments, you will learn a lot. You will learn a lot. Okay, so by the way, when this is an image and you don't have exactly, you cannot make this as small as possible for an image website. So only the smallest number that you can get is one, right? Because one pixel. So therefore, you have to put one there and one here as far as an image is concerned. So this is how you do the derivative. But now, when we compute these things in the image, we have to express that as a convolutional kernel. So what is the convolutional kernel for this? So you can see, I think you remember that we take this axis as the x-axis for images, and this axis is the y-axis for images, right? And then you can take this point as x. We don't have to write x node because we are lazy. This point is x in the image. Okay, of course, it has pixels, right? These kind of pixels are there. So maybe these some pixel I'm drawing. These are pixels. These pairs are pixels. So what I have to do is I have to this locate x. So I need x plus one. So if this is x, for a particular y, for a particular y, let's say that this is that y, and that we want. And what we do is we have to take x, and we have to take x plus one. That is this pixel, and we have to multiply by these coefficients. So fxy's coefficient is minus one. Fx plus 1 y's coefficient is plus 1. So here you can see, here there's a 1, right? That one is this one. And this one, this minus sign, minus 1 is this one. So you can see, we can express that as a convolutional kernel. Very simple. And then we can use the same filter 2D that we used when we did Gaussian filtering to obtain this value. This is quite exciting, actually. But one thing is, this uh, kernel, this kernel, we call it a kernel, I hope you remember. This kernel is not symmetric. I mean, there's no well-defined center for that. So we don't like those things when there's no well-defined center. So what we do is, instead of that, we like to have a so-called central difference formula. That means we will consider three pixels, put minus one there, put zero here, put one there. So that you are computing the gradient exactly at this location, at this x value and at this y value in the image. I hope it is clear to you. Now you can see we can obtain the derivative of an image by running a convolutional kernel. So this is I gave you so this. Okay, so now this is from an exercise from the previous uh, lesson also. Now you can see the tiger image, right? Tiger image there is there. That has vertical edges here, right? There is a vertical edge, vertical edges, vertical edges. And then these are sort of horizontal edges, right? Horizontal edges. So here you can see the vertical edges. Here you can see the horizontal edges. Remember, this axis is the x-axis, and this axis is the y-axis. So let me give you names. This is A, this is B, A and B. Okay, I'm asking you, which one is the partial derivative of this image F with respect to x? A or B? Let me see whether you can answer this question. Hmm. See, I'll take a poll. Okay. You can see it, I hope. So please answer this. Partial derivative of f. Okay, I had written df by dx. That's okay, I think. You understand what it means. Which one is it, A or B? A minute or so. 23 people have answered from out of 54, 52, 25, 26, 27, 30, 31. Maybe one more minute. Okay, let's stop this. So let me give you the answer. Mm, Actually, this is detecting this A is horizontal vertical edges, right? Vertical edges. B is horizontal edges. And now to detect an edge, that means these are vertical edge. You can see a vertical edge is a transition from dark to bright, or bright to dark is also okay. And we it is negative value. Bright to dark is also okay. This is a vertical edge. Those are the ones that have been detected here. In this image, what are the things that have been detected? In this one, it has detected dark to bright, dark to bright, or bright to dark. Right? This is what has been detected. So I have told you that a kernel will look for things that looks like the kernel. Look for things that looks like the kernel. So therefore, to detect these kind of edges, you will need a kernel that looks like this. So right, 1, 0, minus 1, right? 1, 0, minus 1. To detect things like that, or the opposite is also okay. And detect things like that, you will need 1, 0, minus 1, this kind of a kernel. Yeah. So from this you can see, and remember, this is our x direction, and this is our y direction. That's our convention. So therefore, the correct answer is A. That's wrong. Correct answer is not A. Correct answer is B. Correct answer is B. And that's the correct answer. Because in vertical downward direction, you detect horizontal edges. Yeah. Okay. So I'll share in the poll and share the results. You can see some of you have gotten it wrong, right? So most of them have gotten it wrong. Yes. So okay. So I hope that this question answers some of these questions that you may have gotten wrong. Okay. Let's move forward. So I hope you can see that. So this is the thing, and this is the kernel. So of course we don't like this kernel, and we will want the central difference formula for this. Yeah. But one thing is, people design these kernels to get rid of noise source. So therefore, people design the private kernels, all minus ones. If you would, rather than considering one column, they consider three columns. Here, rather than considering one row, they consider three rows. And so we have already seen emphasis on the central row, central column, emphasis on the central row in this one. Yes. So now we can. do a bit of an exercise and see. Actually, we have done this. Now we will do that again. So I hope I have some kind of good image. Let me see. I have the image folder, pictures. To do this edge detection, you need to have a good image, right? That shows us what they are. The Seagate image was good. Um, yeah, I have the this image. Uh, Let me use that. Let's get started with Visual Studio Code. I hope the Visual Studio Code is working on your machines rather than using Colab or something. Um, it's yes, okay. So I have the file here. So let me open the this image in grayscale, and of course this assert f is not done is so important to see whether this image has been opened. Uh, in the meantime, I will send this image over your Zoom chat. Okay, if you want the exactly the same image, you can use that. But just run, that's fine. So this is the giraffe image. So let's oh, it's prompting me in Chinese. So I want to define the kernel as I will say dx kernel. Okay, dx equals np.array. So I will define it as a central difference formula kernel, vertically downward. So in the top, I should have -1. In the middle row, I should have 0. In the last row, I should have 1, right? And as type float 32, this you know. So I will print dx and show you dx and show you what that looks like. Yeah, that's dx. So dy, so similarly dy, and I will print the dy and show you what that looks like. Okay, so dx and dy, yeah, okay. Now to get fx, yeah, fx, cv filter to d, you can give the data type d and d with dx, fy is dy, and then we can do subplots. Uh, uh, I want to p, p comma x equals PID subplots. I want to have the three of them. Okay, and something. And then in AX0, I will show the original one. Remember, we have to give Vmin and Vmax, right? Vmin and Vmax. That's the original image, and FX. PID.show. And one thing is here also we need to give Vmin and Vmax. But for that, one little thing has to be done. That is, we have to normalize that. Otherwise, you will not get the proper values seen. Or otherwise, you can do something like um, normalize. Uh, you are normalizing it. Now it has been normalized. Then you should be able to see these things, this giraffe image. Yeah, you can see in the giraffe image, beautiful giraffe image. So you can see x direction means vertically downward, and y direction is horizontally rightward. You can see the vertical edge is directed here, horizontal edge is directed there. I think it's beautifully done, right? I want to get rid of this access of. Uh, so AI prompting is good, right? I can quickly get these unnecessary things done. Yeah, it is indeed beautiful. So I'll let you type this. I give you a second to type this one. Please get this working and you feel very happy about it, what you have done. Please do not hesitate to ask if you have any question. Let me type a title for this, otherwise I will forget this. Central difference right, markdown also. This markdown also I don't fully like. Okay, maybe I should boldface it. That's good, right? Okay. Any questions about this? Are we all okay? All right. Now let's use the Sobel filter to do the same thing. So it's quite easy. I will select the whole thing. I'm actually happy about this giraffe image. This we have done, okay? This we have done in one of the very first lectures, but I will do it again. So rather than having this dx, we had used the Sobel filter, right? CV dot Sobel. This 10, I hope it is okay. Let's see this. Let's print and see. So 0, 1. I think we may have to do a change there. Sobel. Oh, CV Sobel. Sobel. Oh, they turned out to be very large. Kernel size is 3.1. I don't know what this is going to happen. I have to delete these things, I think. Like this you can do, but CV Sobel also can give you that. Let's try that. So docs.open cv.org, and when you can go to some of those docs and type Sobel here. Um, Sobel filter, dxdy. Oh, it has like that, right? Sobel operator combines Gaussian smoothing and differentiation, so the result is more or less resistant to noise. More often, the function is called with x order 1, y order 0, kernel size 3. This is what we did. Sobel, yeah. Oh, I know. You cannot generate a kernel here. You can directly filter using this. Yeah, that's a mistake. So that's a mistake. See this Robel? Yeah, this is what it is. This is what we want. Yeah. Okay, I'm very sorry about that. You directly get that, okay? So now let's see whether this is correct, because our interpretation of vertical axis and horizontal axis sometimes is different from this. So normalization, I forgot. Now it's okay. So wave filtering has been done and the normalizing, it's good, right? So this is Fx and Fy. So one thing is, by using this one, we can compute the magnitude of the gradient. So plot that also. I'll give 4 columns here. Grad magnitude, gradient magnitude. I can get, you can do it like that also, but I can use NumPy to get that. NP SQRT, SQRT, you can square it and with the square root. This nonsense is not required. I think it's because grad magnitude is equal to, you can use that. Otherwise, you can use NumPy NP. Then you can see what it is. NP SQRT fx square plus fy square. That's a gradient magnitude. So let's normalize that also. Otherwise, you cannot display that grad mag equals CV normalize grad mag and then print to grad mag also. Gradient magnitude and this too much. I think we have 16 and 4. So with the gradient magnitude, you can see the magnitude values have been quite high at the very sharp transitions. So that is of the gradient. So you can see clearly that the edges can be whether the horizontal or vertical. You can see the gradient magnitude. Okay, any questions about that? The Sobel operator and computer gradient magnitude also.
Excuse me, sir.
Yes.
Yeah, so the output generated the black and white, some like it's mean negative and positive values. The black and white colors are generated in this according to this. So can we do this to the color image also? That means by
Yeah,
color.
that's a good question. So here we have opened the image as a grayscale image. You are right. We have opened the image as a grayscale image, and then when you get the gradient, you see gray values. Here you can see very high values for edges and very low values. If you take a color image, there is R plane, blue plane, and green plane. No? So you have to detect edges in each of the planes, and then you have to have some mechanism of combining them. Otherwise, you have to detect the edges only on a grayscale after converting to grayscale.
Okay.
So these are transitions in intensity, right? But if you want direct transition in color, then you can use one of the color planes. One plane only. You cannot use all three color planes.
Okay, sir. Thank you.
Thank you for that question. So what you would do is you will open that image as a color and separate it into different planes. Then you can see the green edges, blue edges, and red edges, one at a time. That's a good observation. Okay, so let's go back to the question. So now you can see this is what we did. So if you take the gradient, it has two values, right? The x gradient and y gradient. So that's why we have to show both of them at each pixel. So we use this special operator called nabla. Mathematical term is gradient, grad operator, grad def. So it has two numbers. That means at every single location you have two numbers. That means at every single location you can draw an arrow with a certain magnitude. That's the magnitude of the gradient, and a certain direction. That's the angle of the gradient, like this. So you can see the magnitude. This is exactly what we used in our computation with NumPy, and you can see that the angle is also important in that case. So this is how you compute the angle. So for this one, you can see it's a horizontal edge. You can see the partial derivative with respect to x is 0. This has some value, right? For a horizontal edge like that, this is a vertical edge. So the gradient will be in this direction. That means there's an x gradient. Y gradient is 0. Remember our sign convention is this is our x direction. This is our y direction. For an edge like this, now here you can see the edge is sort of like that, and you will have both non-zero values. Yeah. Okay, so you can do fun things with this gradient. So you can look at these results of this paper by clicking that. SIGGRAPH is a very important conference, special interest group in graphics. Yeah. All right. Now let's see how to detect these edges using noise. And when there is noise, what to do. So you can see this is a one-dimensional image. You can see these areas are dark and this is bright. But there is, you can see some noise is there. It's not a clean image, some noise. Remember, this is a scan line. Now, one-dimensional image shown as a function of x, the intensity. So if you want to do the d by df of this, you will get all noise. The reason is now consider noise frequency. Yeah? So noise frequency is like sine, very high frequency, sine omega naught t or something. Okay, and this omega naught is like 10 to the power 1 million radians per second. 1 million rad per second or something, right? That's a large value. So like the noise has high frequency, right? So if you do d by dx, d by d sine omega naught t by dt, do you remember the answer? You will get as the omega naught will be multiplying that. Omega naught sine's derivative is cos omega naught t, right? So you can see if your frequencies are high, very high, that means like noise, you will have this multiply at the front after derivative. So that's why these noisy things are like so amplified because of this. So this is not good. So that means you cannot get the derivative on a noisy image. It's not possible to do. So that's why we had to first get the image and you filter it with the Gaussian kernel. I hope you remember the shape of the Gaussian kernel. We constructed this and so on. When you run this, all the noise will be sort of gone. And of course, the edge will also be slightly smoothed out. That's okay. So we show this Gaussian smoothing with the convolution operator. The convolution operator is a star, as you remember. And this you can do the d by dx on this. When you do d by dx on this, corresponding to the edge, you will have a peak there for sure, but it will have some width also. There is a little bit of problem, but I mean, this is what you have to do when you have a noisy image. But then we notice something that all these two operations, the d by dx and the Gaussian smoothing, these are linear operators. So if they are linear operators, it's like 3 times 5 times 2 or something like that multiplication, right? What we have decided to do is done the 5 times 2 multiplication first and done this multiplication next. Oh, all right. We can do this one. Do the 3 by 5 multiplication first, and then using that we can multiply that by 2, right? It is possible. I mean, this is correct. So for the linear operators also this operation is correct. So therefore, we can first differentiate the Gaussian kernel and convolve with F. The reason is this. Now, if you take a 1000 by 1000 image, and if you run the Gaussian kernel for every single pixel, you have to do that Gaussian filtering, right? So if the Gaussian filter is 5 by 5, 25 multiplications at each location. So it will be like 25 times, 1000 multiplications will have to be done. And then once again, now you have to do the derivative kernel, again that many computations. So that's stupid to do like that. But if you convolve the Gaussian with the derivative, which are small filters, maybe small filters, maybe 5 by 5, then that operation is very less expensive. And then you uh, take that resulting filter called the derivative of Gaussian filter and apply that on the image. There you go. So rather than doing this, Gaussian convolving first and getting the d by dx next, we can do the d by dx of the Gaussian and then convolve with the image like so. So this is the d by dx of the Gaussian filter. I will show you what that should look like. All right. So let's consider the Gaussian first. So I hope you remember in 1D, yeah, 1D the Gaussian will look like this, right? Gaussian will look like this. What is the d by dx of Gaussian? So this is d. What is d by dx? We have to consider the slope, right? That's all, right? D by dx. We have to consider the slope. So how does the slope work here? So here the slope is 0 here. Here the slope is 0. It's horizontal line. Here the slope is 0. It's horizontal line. The slope is small positive number here, large positive number here, small positive number here, small negative number here, large negative number here, small negative number there. So therefore, we have to do 0, 0 again here. Maximum will be somewhere here, and then it will look like this, right? And similarly on the other side. Can you see this is the derivative of the Gaussian kernel? That's what you have drawn here. And then you run that as a convolution on the image, and then you will be able to detect the peaks to find the edges. I hope this part is clear. So we are using the fact that the derivative operator and the Gaussian filtering are both linear. So therefore, they can be interchanged because of the associative and commutative rules of convolution. Okay. So these, if you do that, these are the filters that you get. Can you see that structure in this filter? Negative dip and the positive dip. These are the two-dimensional filters, and yeah. If you like, you can construct a Gaussian and run the central difference formula on that and obtain this. But I will not do that. Yeah. Okay. Okay. Then on that. Are these filters? They are separable also because you can separate them into a totally x dependent function and totally y dependent function. So separability also helps us to increase the computational speed. There you can see they are separable. Right? This is a function only of x. This is a function only of y. That's a Gaussian. So the others are also separable. Okay, so the scale of the Gaussian derivative field also matters. So you can see the 1 pixel, 3 pixel, and 7 pixel. That's the sigma of the Gaussian. So you can here you detect very fine edges. Here you detect coarse edges. Here you detect much coarser edges by changing the sigma of the Gaussian smoothing. Smooth derivative removes noise but blurs the edges, also finds edges at different scales. Yeah. So some small thing review about that. Gaussian removes high frequency components. It's a low pass filter. We have seen that. We did that with Mr. Tom Cruise's image to get a blurred version of that. Can the values of the smoothing filter be negative? No. The smoothing filter's values have always to be positive and they must add up to 1. What should values sum to 1? One constant regions are not affected by the filter. So assume that you have white wall and you apply the smoothing filter on the white wall. You should get white. So therefore, constant regions must not get affected by that. Derivative filters are derivative Gaussian, and can values of filter be negative? For sure, they can be negative. So these dark areas are negative. These dark areas are negative, yeah, and these are positive. What should the value sum to? They will sum to 0 because no response to constant region. Constant region has no slope, right? No gradient. It's 0. So high absolute value at points of high contrast. Yeah. Okay. Any questions about the smoothing and derivative filters? Okay, that's good. Now let's look at the so-called Kenny edge detector. So although we can get derivatives from that, we don't have a thin line representing the edge. What we want is a thin line of 1 pixel width representing the edge. This is what the Kenny edge detector can do due to Kenny, a paper published in IEEE Transactions and Pattern Analysis and Machine Intelligence in 1986. This is the best journal of all of engineering, highest ranked journal of all of engineering even right now. Yeah. Filter image with derivative of Gaussian. Find the magnitude orientation of the gradient. You don't understand any of these things now, but when we do it, you will understand. Non-maximal suppression, thin white ridges down to single pixel width, linking and hysteresis thresholding. Define two thresholds, low threshold and high threshold. Use high threshold to start edge curves and low threshold to continue them. Okay, let's do that. This is a bad image. So you take the original image and you run derivative operator. This is the magnitude of the gradient. So you can see all the edges are present in this, very light edges and very strong edges. So we threshold and we retain only strong gradients. We retain here. But the problem is that each of these edges has a thickness. You can see the thickness. So edges slowly transition from the dark to bright, for example. And because of that slow transition, if you run a derivative operator in the graph, there's some width, right? There's some width of the edge. That's what you see here. So you want to get rid of that width. So to do that, there's an operation called non-maximum suppression. So we don't do that on our own. So assume that this is an edge and you draw a perpendicular line there and you pick the maximum there. So then you can thin it down to 1 pixel. So you thin it down to 1 pixel. That's good. So now what we wanted, that means 1 pixel representation of the edges is there. But unfortunately, the edges are not continuing. They have been broken. So we don't like that. So this kind of problem, pixels along the edges didn't survive thresholding. So therefore, we had to do something that is called hysteresis. This means something like this. Now assume that an honorable minister is going into a restricted area. When the ministry is going behind, not so powerful people, the Goliaths, or can also go, right? But can the Goliaths go by themselves into the restricted area? No. Or when the honorable minister is not there, people say, no, 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 you cannot go. But when you are going with the minister, the Goliaths, the low power people, low strength edges can also go. So the idea here is when there is a high strength edge, low strength edges connected to the high strength edge can pass. Otherwise, low strength edges are discarded. Okay. So use a high threshold to start the edge curves and low threshold to continue them. So this is the original edge, then high threshold strong edges, low threshold weak edges, and then hysteresis threshold. Then you will get some edges continuing. So I want to show you this by a code. I show you that by writing. First of all, I'll write the Kenny edge detector, uh, but I will not code from scratch. I will use the existing function. Kenny edge detector. Let me. I have it. So import CV2 as CV, import import numpy as NP. Okay, all this is fine. So image as the image, I will get im equals CV dot imread I will get this image called the girl. I have an image called the girl, a beautiful image. So I will send that to you. So as you know, because you are participating in this class, as a gift, you get this my collection of very beautiful images collected over many years with a lot of hard work. Here is a girl's image. Yeah. So you obtain that image, and then we have to run the Kenny edge detection operation on that. Uh, it is very easy. It just equals C dot Kenny. So you can put like 50 and 100. I will explain these two thresholds later. Understanding these two thresholds is very important. So first of all, I will use OpenCV display to display this. CV dot named window. First of all, I will say image display or something, window auto size. CV window auto size. Let's call it display. Display is okay. And then in this window, we can use CV in show first. Let's do in the original image in, and then we wait for a CV key. CV dot wait key 0, and again wait for a key, and then CV destroy all windows. So one thing is, if when you're using this OpenCV Windows, your kernel can crash if you try to do some funny things. So run this. You can see this here, the girl's image. So if you hit a key, you will see the edges. So I didn't use the same name. That's why I got two windows. But I did not explain about these two thresholds. I will explain about those thresholds with another piece of code that I will not. Okay, maybe you can try it out. I will give you a second. Please try it out. You'll be very happy. So it's very important to do this right. So in this now. I hope that you would have gotten this right. So now I want to explain the thresholds. High, high threshold and low threshold can. Okay. So that one I will not give you time or something. I will just put that. Okay. Put this code and run because I have some tracker bars and so on. So same girl image. So to get that open, I need to copy this because I have now a different folder where the images are kept. Okay. So color images are not possible. There's no problem. It's possible. There's no problem with that. So this one allows me to change the thresholds. So you can see what I want to show here is when the high threshold is small, when the high threshold is small, lot of edges are past the threshold, and then they all are included in the edges. But when my high threshold is high, most of the edges disappear. They don't pass the threshold, so they cannot. They don't start. They don't start. Okay, let's keep it at some point. Now my low threshold is very high. That means I do not allow the goal as to continue with the high threshold. But if I lower it, you can see the high thresholds, the high strong edges that start grow. They grow. Because now I allow go layers who are connected with the powerful honorable minister can also pass through. Can you see that? Can you see the effect of the low threshold and the effect of the high threshold? I will make this available to you. Yeah, this is what happens. I forgot to destroy all Windows line. When you don't have it, that crashes. Now I have to restart. That is okay. That's a good time to go back to slides. Now you can, I think, hope you can understand that in the Canadian data, we compute the X gradients in the image and we compute the Y gradients in the image and then find the gradient magnitude and then we have to do gradient non-maximal separation. Remember, we have to thin down the edges and the linking and thresholding hysteresis, define two thresholds low and high, using the high threshold to start the edge curves and low threshold to continue them. I hope that this is clear to you now. Any questions? Okay, we can move forward. Now you can see these image gradients versus meaningful contours. Now we have gone to a slightly more meaningful edges using the Lineage detector. So but you can see the human segmentations are still much better. So now the deep learning methods are used to for detection. They are much better now. Okay, now let's look at the corners. So these are corners, as you can see. But mathematically, okay, how do you define them? Edges, if you take an edge, let's take a tabletop. Okay. Tabletop. Tabletop. And this area, as you can see, this is an edge, right? It's an edge. That's an edge. That's an edge, right? It's an edge. And this is an edge. What are corners? This is a corner, right? This is a corner, corner, and a corner. You can see at a corner, there are two perpendicular gradient changes. At an edge, there's only one gradient change happening. I hope you can see that. So that's what we will use to mathematically characterize this. So why are these corners important? We have two images. If we have, we can perhaps combine them. So we detect features, extract features, match them, and then align images. So I will give you an image alignment exercise as an assignment. And for this, these corners are important, and these corners must be what are the good features? They must be repeatable. That means if you detect them on the first image, they must be seen in the second image also. That's the repeatability. Salience, each feature is distinctive. Each feature must be different from the other feature. Compactness and efficiency, many fewer features than image pixels. Locality, a feature must occupy a relatively small area. In image, robust to pattern occlusion, not you don't need 200 by 200 pixels to represent one. Yeah, that's the idea of it. So they are important for image alignment, 3D reconstruction, motion tracking, robot navigation, indexing, and database retrieval, object recognition, and for all these things, these codes are very useful. Okay, now if you take this image, these two images taken by NASA Mars rover. Where is the rover looking at in the second image? See, as a human being, you cannot do that. But if you detect features, so-called SID features, we will study about that. You can see where the Mars is. So let's look at this corner direction idea. Why should we should easily recognize the point by looking through a small window? So in computers, although computers are very powerful, they have a very local view in regard to these images. So shifting the window in any direction should give a large change in intensity. So now let's think about the flat region. Now you can see the dark is a corner, but the window is inside the corner part of the image. Yeah. So if you make a slight movement like this, slight movement here in any of these directions, will the underlying image structure change? I'm on top of this dark area. If you slightly change, it will still be the dark thing underneath the window, right? Nothing changes. But if you consider an edge, if you move vertically, nothing changes. You see the same thing if you're moving vertically. But if you move horizontally, you can see the intensities within that window keep on changing. Do you understand this concept? Okay, I hope. But if you look at it at the corner, even if you do a slight change in vertical direction or horizontally, any other direction, what is underlying of this core patch of this window will change. This is what we will consider in corner detection, significant change in all directions. Okay, so let's mathematically characterize that. Now let's see this. So we have to slightly change the window, right? That's all we have to do. So now let's take this image window IXY, and we consider an image XY belonging to some window. So we consider that this as that uh, uh, square window. And then what we do is we slightly change the location of that window by small u and small v in both the direction, in x direction u, y direction v, and then observe what changes that happen. If u and v are 0, what is the value of this function? So let me give a little poll for that, so that I know that you are comprehending what I am saying. Yes, that would be. Oh, something is wrong with that. Let me forget about this. So maybe you can type in the chat. Let me ask that in the chat. So maybe some of you can type. When u and v are both 0, what is the value of u of v? Very easy. What is the value of uv? So please give a quick answer to that. Can some people try the answer before I give the answer? Room chat. Some people are correctly answering. Thank you for that. Thank you. Thank you. Yeah, three, four. Yeah, four people answered. Thank you. That means you're paying attention. That's good. One more person, no, five, 1, 2, 3, 4, 5 people who answered. Few more people, please answer. Okay, that's good. I'll give you the answer. So this is very easy. If U and V are both 0, U and V are both 0, you can see this also becomes IXY and they cancel off. This will be 0. So this is IXY when U and V are both 0 and you subtract IXY, you will get 0 there. So you can see that's why when both of U and V are equal to 0, that this is the dark pixel, 0. And you see that it's dark, it's 0. So if you move the window around, you get different values. For example, at 3, 2, that is a window has been moved by 3 and 2, you get the value. Because we want to find how this function behaves for small shifts, U and V. Let's plug in this equation. Okay, but before that, how did I get this one? I'll explain using the theory that you know in A levels. Now let's consider the how to use the Taylor formula to get a value of a function at x node plus h or something, okay, which is a small number. So the best approximation is fx node. Fx node is because small number, this is like let's say 0.001, 001. It is almost fx, right? And then what is the next term? Next term you get as h times f prime next, derivative of x. That's my next number. Of course, you can keep on writing them. Next number will be h divided by 2 f double prime x, second derivative of it. And so on. So we don't use this formula here. We have used the first order. What that means is we have disregarded the higher order terms. Like this term, okay, that term we use. This we use, this one we disregard. Since these are in two dimensions, you have the partial derivatives because you and we are there. So Ix is the partial derivative in x direction, Iy partial derivative in y direction, and we know how to compute them using the Sobel operator. Okay, so now what we need to do is we'll take this and we put it here. Like so. So when you put it, you can see this Ixy cancel off, right? So you have Ixu and Iyv. That's what you have. And then you can expand it like that. I will not go through the expansion. You just have to square it. So you get these terms. So the quadratic approximation can be written as a matrix multiplication also. So this is our matrix multiplication. It's very important. So this matrix is actually called the second moment matrix. Second moment matrix. So you can see it's the summation over a window ix squared, summation over a window iy squared, summation over a window ixiy, summation over a window ixiy. So you can see we can construct this M matrix at each location of the pixel. That means at each location we will have four numbers: M11, M12, M21, M23. M11, M12, M21, M22. Like the four numbers are there at every single location. The sums are all the pixels in a window, so, but we have to thumb them over window, otherwise this cannot lead to solutions. The surface EUV is locally approximated by a quadratic form. It's like a coconut shell. But if you look at in 1D, so 1D, let's take this, it's a square. No? So you can see, right? This square, right? It's a square in 2D. What's a square in 1D? Square function in 1D is like this, right? It's like a coconut shell. It's like x square. That's like coconut shell, but since this is square in 2D, it's like a coconut shell actually in 2D. You can see that that drawn here, right? This one. So this is uh, when you multiply, you can see you get u squared because there's a u here also. V squared there because there's a v here also. That's the value of this matrix formulation. So this M is supposed to be, I think, positive definite. So M is like that. So first consider the axis aligned case. Gradients are either horizontal or vertical. If the gradients are horizontal or vertical, ix squared is high, iy squared is high, right? So it will look like the A and B, and the off diagonal elements are zero. If either A or B is close to zero, then it is not a corner. That means it's like edge. So look for locations where both are large. So that's fine. Consider horizontal. If you consider horizontal slice EUV and UV times UV is constant. So this is an equation of an ellipse. So what we can do is we can take this M and convert that to a simpler form, lambda 1 and lambda 2 with the rotation in various matrix and rotation matrix. This we have studied before, what these rotation matrices are. No, we have not studied, right? We have not studied, yeah. Sorry about that. But the axis length of the ellipse are determined by the eigenvalues and the orientation determined by R. So these are the eigenvalues lambda max minus R and lambda mean minus R. These are the lambda values. These are the axis lengths of the ellipse determined by the eigenvalues and the orientation determined by R. So if we plot that on an image, now here you can see, so you can see that there are corners, and for corners you have to get circles. For other things, like for example, this is clearly a corner, this is clearly a corner, this maybe, I'm not too sure, maybe this is an edge. Edges you should get elongated ellipses. So you can see for edges, you have elongated ellipses, like here for example, for corners, you will have circular like ellipses. So this is the second moment matrix. And by using the second moment matrix, we can characterize edges. So you know that when M is there, you can compute lambda 1 and lambda 2, the eigenvalues of the M matrix at that location. Both these are small, it's a flat region. If one of them is large, it's an edge here and there. If both are reasonably sized, we have a corner detector. Corners, lambda 1 lambda 2 are large. Lambda 1 is generally equal to lambda 2, and E increases in all directions in this case. So this is the theory of corner detection. But one thing is, computing these eigenvalues is expensive. Therefore, in 1988, Harris and Stevens came up with this equivalent formula, determinant of n minus alpha trace of m squared. Determinant of m minus alpha trace of l squared. So alpha's value is the experimentally found, I think, 0.04. This is a very, very good example of corner detection. So when R is small, R's magnitude is small, somewhere here, it's a flat region. When R's magnitude is less than 0, it is an edge. You cannot distinguish between this edge and that edge, it's an edge. And then when R is greater than 0, it is a corner. Is it okay? This is called Harris criterion, and we have to memorize this and this number also we have to memorize. So when you have to do the Harris corner detector, we compute the derivative at each pixel location, compute the second movement matrix M in Gaussian window around the pixel, and then we formulate M here. Remember, this M is for every single pixel. Okay, and then compute the corner response R, that is the determinant of M minus alpha times trace of M square. And then I will show you those. For example, if you take the corner response, you can see at corners the response is very high, it's red, and other location is it's small. So then what we do is we threshold this R value, and then we find local maxima of response function using the so-called non-maximum suppression. So here is find points with large corner response R greater than threshold. So you have threshold at that. Then you take only points of local minima of that local minima. So you can see some dots are there. I hope you can see it on your screen that some dots are there. So when you superimpose those corners, you can see the real corners, they correspond to real corners like the horns, like the horns of this cow image. Yeah. Okay, so let's take a very brief break. Maybe you can take a 5 minute break at okay 11:55. We can meet 11:55. Yeah, we can meet again. I'll post the recording. It's a 2 hour class today. Okay, so we are doing Harris corner detection. So you can see I am opening this so-called building.tif image. I will share that image with you. It's an image where corners can be easily seen. That's why we use that image. Thank you for alerting me that I am not recording that. Okay, here's the building.tif image. So now I'm using the Sobel operator. So you can see it's coming again and again, right? And I'm getting Ix. That means the partial derivative in x direction, vertically downward. Iy, partial derivative y direction, vertically downward. So I have Ix and Iy. Now I need to construct the M matrix. So remember in M matrix, Ix squared, Ix Iy, Iy squared, Ix squared, Ix Iy, Ix Iy, Iy squared. But of course, we have to sum them over window. That means we have to do Gaussian blurring. So I will not spend time in coding them individually. So this is what it is. So I pick a sigma and kernel size 11. Then I Gaussian smooth Ix squared, Ix Iy, Ix Iy. Oh, yeah, Ix squared, Iy squared, Ix Iy. Then those two things are equal, right? Because we can see that in this M matrix, these IXIY and this is IXI, they are equal, right? So you can see this Gaussian window summing is there. So exactly what we are doing this. But one thing is this all these things are of the size of the image. For all the elements in the pixel, I am doing it now. And then let's compute the determinant that is equal to. So we know how to get the determinant. So we get M M11, M22 minus M12, M21. So that's how you get the determinant, right? Do you remember how to get the determinant? So of a matrix. So determinant. So if you have something like A, B, C, D, this has four elements, no? A, B, C, D. How do you get the determinant? A, B minus B, C, right? That's the determinant, right? Very easy. That's exactly what we are doing here. Here, that's a determinant. And we know in the trace, trace trace equal to is M11 plus M12 the diagonal elements. Then the Harris measure, so it knows what I did. Determinant R is equal to determinant minus 0.4 trace squared. So this is the Harris measure that we show in the slide. Exactly, I'm doing exactly what's there in the slide. So I want to develop your trust on the slides that they do work actually. The important knowledge and they work. So determinant minus alpha times trace squared, alpha is 0.04. So that also we have put. So now Harris measure is there. Now there are some non-sensible things, not non-sensible, annoying things where they had to detect the peaks and all sorts of things. For that, I will not spend time right now. I will copy the code and so important parts are done. So this is the displaying part. I'll show that directly. So we can see the original image and fx, ix, iy. You can see this is the x directional gradient. You can see that vertically downward edges and these horizontally rightward edges. And then the R measure, you can see definitely the core for corners, it has high values, right? Corners, it has high values. And then I have done the thresholding and the peak detection. So, and then I am plotting the corners. And then out of that non-maximal suppression thing, all these things and corners have been extracted and plotted. You can see this, yeah. So that is the Harris corner detector. So I will keep this shown for a little while. This non-maximal separation part, I did not show. I'm using this, I think, SK image features, peak local max. Okay, I hope you are happy about this. Harris corner detector, you have been able to detect corners by writing code from scratch. Otherwise, you can use OpenCV's Harris function also. Harris corner detector is there implemented in OpenCV that you can do and see. Yeah. Okay, now let's study these corners further. Now, we want the location of the corners to be invariant to photometric transformations and covariant to geometric transformations. What that means is, even now you can see in this image, the cow has been rotated. Even if you rotate, the corners have to be detected. And if you change the intensity of the image, that means photometric transformations, the corner location should not be changed, invariant. When you are rotating the image, they must be covariant, like the image it should be rotating. So invariance means the image is transformed and corner locations do not change. Covariance means if you have transformed the versions of the same image, we should detect at the corresponding location. That is the invariance and the covariance that we are looking at here. Okay, so question for you. Is Harris corner detection invariant to affine intensity changes? This kind of thing. You take the image, multiply by some value, and you add some value. Is it invariant? Think about it, like in Harris corner detection, how do we do it? We run the gradient operators. Are the gradients sensitive to, if you add 5, is the gradient sensitive to that? No, because when you run the gradient operator, this constants gets cancelled. Is it sensitive to this alpha value? Yes. The gradient the gradient will be there, and the value of that gradient will be multiplied by that number A, right? So therefore, some things that did not pass threshold will pass if you multiply the image by some number. So therefore, it will be partially invariant to affine intensity changes. So you would do a color change like that, that's an affine intensity change. Only derivatives are used, so therefore invariant into shift. Variation shift is there of this the derivative operator. So therefore, intensity scaling is there, I equals I. Then because of that, your gradients can become large. So therefore, some points that did not pass the threshold may pass the threshold in the opposite direction. If you reduce the alpha A value, some points may not pass. So therefore, partially invariant of intensity changes. That's why we call it partially invariant. Now take the translation. You are taking the image and moving the image. You can see the image has been moved to this location. I mean, it does not matter, right? The corner will also move. So derivatives of the window function are shift invariant. So corner location is covariant with respect to translation. This is fine. I think you can understand it. Rotation. So we have rotated the image. You can see the corner that was there like so has been rotated like that. So the ellipses that we talked about, this lambda 1 and lambda 2 values, those will also rotate. So therefore, the corner will be there at the particular location appropriately. So second moment ellipsis rotates, but its shape, that means eigenvalues remain the same. So corner location is covariant with respect to rotation. That is also okay. But what about the scale? Now here, I am showing you a corner. So you can see this corner here. So you can see the corner here. Is the corner. And you can see the window size, right? It's a small window of this size. That's a corner. But assume that you suddenly zoom the image. You zoom the image, and within that window of ours, which remains the same size, what do we see? We see a straight line. Do we see an edge? Do we see a corner? No, we see a straight line. Here also we see a straight line. Here also we see a straight line. So therefore, all points will be classified as edges. Corner location is not covariant to scaling. So therefore, the Harris corner detection is not scale covariant. This is a big problem. So therefore, we have to solve that. To solve that, we do a blob detection. Okay, now let's see blob detection. So what we want to detect are large blobs like that and small blobs like that. We want to detect all of them. Yeah, these are called blobs. So they are like dark patches in sort of a bright background. These are what we are going to detect. So this theory is very important. This gave rise to the blob detection theory, and it is gives rise to scale invariant detection using the so-called scale space extrema detection. There's a theory called scale space. Okay, so that is what it is. Feature detection with scale selection. We want to extract features with characteristic scale that is covariant with the image transformation. So we can see this church. I think has been zoomed out in this one. I think the text is zoomed out. So they have plotted the same size as the circle here. So they have some function. I don't know what that function is. I know that. I will tell you what that function is. And then that has become a maximum at scale 10.1 in this image. It is a maximum, right? The function is a maximum here. That's a peak. In this image, it is maximum at 3.89. So our question is, can we come up with a function that maximizes at the right scale of that patch? And if we can, what is that scale value? Is it 10.1 or 3.8? What is that value? And if you know the value, we can locate the window properly, and we would be able to assign a scale to the blob that we detect. So this is what we want to do. All right. So this is the kind of filter that we use to detect blobs. Convolve the image with the blob filter at multiple scales and look for extrema of the filter in the resulting scale space. Now we have been looking for maxima in the x and y directions. X and y directions, right? Let's call it this x direction. Let's call this y direction, and this is sort of my image, right? This is my image. So that we have been looking for maxima in this xy space. Now we don't do that only. We will you have another axis called the scale axis. Scale axis. So we not only look for maxima in the xy axis, but in the scale axis also. Can you see that? That's the mm, uh, that's the thing that we will be doing. Drawing. Okay, I'm sorry about that horrible drawing. I hope you can see what sort of thing that we are doing. So if there is a maximum, okay, we have to locate the maximum in all 3D. So if you locate a point here, it is a maximum in X, Y, and scale. So those maxima, local maxima, are the ones that give rise to these blobs. You can see because we have a particular scale also. The scale is, let's say, 5. Because of that, we can draw a circle of that scale. Right? Can you see that? So for these ones, maybe the scale is 10. I'm just telling some numbers. Not exactly. Can you see that? That's why we can draw different sizes of circles because it has been detected in a scale invariant manner. That blob filter looks like that. So the dark here, some brightness there, and some little darkness here, little bit of darkness here. That's the blob filter. I'll give you the formulas of this filter, and you can do that on your own. So the blob detection, the basic idea, find the maxima and minima of blob filter response in the scale and space. Scale and space. So you can see the maxima here, you can see the minima there. So this blob filter looks like this. You can see it is the second derivative of the Gaussian added in x direction and y direction. Uh, you can see that this formula, we had to slightly change this formula later. So I will show what that we had to do the scale normalization. I will show you that later. So this is that one. So partial derivative of the Gaussian in x direction and partial derivative of the Gaussian in y direction, second derivative. Okay, second derivative. NURT. That's called the Laplacian of Gaussian. Laplacian of Gaussian. I am tempted to do that. I have 10 minutes. Maybe let's do that. Let's do that. Laplacian of Gaussian keyboard. That's okay. What matters is uh, so we'll just construct this and show. Huh? Laplacian of Gaussian in 3D. That's what I want to do. Import numpy as np. Import matplotlib .pyplot as plt. Oh, we want another one. I don't remember that. I'll do it later. So first of all, I'll construct my x values. Okay. Half width of the kernel. Let's take 20 or something. So x equals np dot range being in increments of 1. Okay. Then y also is that. And then I have to construct the so-called mesh grid. I hope you remember the mesh grid because it gives you all x values, all y values. Then I can define the Gaussian and get the derivative. So g is 1 over 2 times np dot pi times sigma squared np dot exp x squared plus y squared 2 sigma squared. This is correct. And divide by g also. The sigma I have defined. Let's say we'll define sigma like 5. That's okay. Yeah, okay. That's g. Now I want to compute gx, right? And gx derivative in x direction. X direction. So okay, now it's what it's doing is it's uh, using a formula, but I want to define a filter and do it x direction. So let me do a Sobel filter and compute that. Okay, I'll define not a Sobel filter, central difference formula. So we'll write kernel x is equal to np dot array minus 1, 0, 1. Remember you did this today. We did this today. So 32, that's okay. And ky is equal to, is correct. Then gx is filter 2D with kx. So then we do not want that. No, we want gxx. Again filter. Then gyy. I don't want gyx. I don't want these two. I don't want these mixed derivatives. I want only these. So log Laplacian of Gaussian. This is Laplacian of Gaussian. So now it's plot in 3D, right? I hope it is working. Maybe there's a problem. Yeah. Oh, I won't access. I don't want access. Remove. Is that it? Uh, what is it saying? Destination type. So this data type problem, okay? So I have to, maybe one of them is float 64. That's fine. So you can see the Laplacian or Gaussian, that shape that we wanted is there, but I want to get rid of this fully clean. See we can, yes. It has to look nice, right? I mean, this, with the access, it ruins the picture. Yeah, it doesn't work. These things I would remove. Get that done. This is the importance of this thing is what's required for plot 3D. I think we have done that when we did the Gaussian plotting. Something like that. So let's see. Rid of all these things. Yeah, now it's okay, right? This is what we wanted. So it's a beautiful one, and is exactly what we have in this one. So this also we can see. This thing. Yeah, you can see that, right? Yeah, so I'll let you see this for a little while. So if someone has brought your computer and they're unhappy that they spend a lot of money for the computer and you show them this plot, they'll be very happy, right? Maybe your parents brought the computer for you, or maybe your partner wrote the computer for you, and if they see this plot, they'll be very happy, right? They will think that you're doing real science here. So you can see what we did here was we defined the kx central difference formula filter, ky central difference formula, the derivative in y direction, derivative x direction. We took the Gaussian and we defined the Gaussian e to the power of x squared plus y squared divided by sigma squared minus. I hope you remember those things. And we filtered once and filtered twice so that you get the second derivative. This is the first derivative. Derivative in x direction. This is the first derivative in y direction. And this is the second derivative. Oh, see, it knows what I am. Second derivative x direction. This is the log. It knows in the Laplacian and Gaussian. Happy body. Okay, so that's all we want to do today. So we have the Laplacian of Gaussian. So next time we will see, after running the Laplacian of Gaussian, how can we get these blobs and different sizes and doing the scale space maxima to finally obtain the blob detector and plot those circles in the blobs. So that's all we want to cover. So if you have any questions, please stay in the class and ask. Otherwise, we are done for today. Thank you very much. Have a very pleasant Sunday afternoon. Thank you. You may log on. I have previously seen videos on face detection and vehicle detection. Is the edge detection used for these tasks? If so, how are these? So the answer to this question is, it is true that edge detection will give rise to a face-like sensation for a human being, but not for the computer. So therefore, for face detection, you don't use edge detection, you use a slightly more complicated ones. In the classical sense, you can use the Viola-Jones face detector, or otherwise you can use face detection, deep learning based face detectors. So we can think about them when we come to that stage. Thank you. So does this assignment is a final assignment or on this day? The final assignment, or do we this assignment, there'll be I think 3 assignments like that, 3 long assignments like that you have to submit on this particular day. So a lot of work in this course, because I want you to do something with this course and enjoy. That's the thing. Any other questions?
Excuse me, sir. Excuse me, sir.
Add more instruction on this. Add more instructions on this. What? Yeah, you have to submit. So the date is I have said March 22nd. I said no. I will extend this. It's not possible to do. Yeah, I know. I can understand what the question is. Okay, let me stop the recording now.